big section here in Math 148 and Business Calculus. In this section, we're going to learn the chain rule. Chain rule is a challenging rule. It's a super important rule. It's the last major rule that you'll need for calculating derivatives in our class. It's a rule that generally students really like once it clicks, but it's also a rule that generally takes a little while for it to click for students. It's kind of a hard one. What it deals with is function composition. So before I tell you the actual chain rule, I want to kind of remind you of some ideas that maybe you learned in a pre-calc class about function composition. So if I have two different functions, f of x equals x squared plus 3x plus 5, and g of x equals 10 plus the natural log of x. There's lots of different ways that I can, informally speaking, put these functions together, but maybe the most useful one is to compose them together. And sometimes you see function composition written like this, f of g of x is how you say this, and sometimes you see it written in a different form with nested parentheses, so f of g of x, kind of written this way. To try to help you see all the different pieces, I'm going to color coordinate stuff. But the point is just this means the exact same thing as this. How do you compose these two functions together? Well, what I teach students in a pre-calculus class is kind of work from the inside out. So first deal with g of x, the thing in blue here. G of x is this function, 10 plus the natural log of x. So I can replace this g of x with 10 plus the natural log of x. This line is identical to this line. I just changed g of x into 10 plus natural log of x because right here it says g of x equals 10 plus natural log of x. And then what I want to do is I want to figure out f of that expression. Well, f of x is given by this blueprint right here. So if I want to put something other than x into this machine f, all I got to do is copy this blueprint, changing all the x's into whatever I want to put into that machine. In this specific case, it's 10 plus the natural log of x that I want to put into this machine. So what I would get is, instead of x squared, I'd get 10 plus the natural log of x that's being squared. And then instead of plus 3 times x, I'd get plus 3 times 10 plus the natural log of x. And then finally, plus 5. If this is f of x and this is g of x, f of g of x, which can be written this way or this way, is equal to this big mess here. And yeah, you could simplify this, you could write it in different forms, but I'm not going to bother. I just want to remind you of some stuff that you might have already known about function composition. So could you take the derivative of this expression right here? Well, yeah, you could. It would kind of suck to do so if I'm being perfectly honest. I mean, this 10 plus natural log of x squared right here is a little bit problematic. But I guess if you really had to, you could be like, all right, it's the derivative of, and then instead of 10 plus the natural log of x squared, I'll think about it as 10 plus the natural log of x times 10 plus the natural log of x, so that I can employ the product rule in the next step. And then I would add to that 3 times the derivative of 10 plus the natural log of x, taking advantage of my coefficient rule, pulling this 3 out in front, and then add to that the derivative of the 5. And then I think you could take this derivative. I mean, sure, I guess I'll do it. I'm not going to show all the different steps because really I'm not too concerned about taking this derivative because the whole purpose of this video is to show you another way. But I can't leave a problem unfinished. So if we're taking the derivative of this times this, you take the derivative of the first thing. The derivative of 10 plus the natural log of x is the derivative of 10 plus the derivative of natural log of x, which is 0 plus 1 over x, or just 1 over x. And then you'd multiply that by this thing left all alone, 10 plus the natural log of x. And then you would add to that, because I'm using the product rule in here, the derivative of this second thing, which is also 1 over x for the same reason this derivative was 1 over x, times this first thing left all alone, 10 plus the natural log of x. And then to that, you'd have to add 3 times the derivative of 10 plus the natural log of x. And I'm getting kind of sick of saying it, but the derivative of 10 plus the natural log of x is just 1 over x, because the derivative of 10 is the 0, and the derivative of the natural log of x is the 1 over x. And then you'd add to that the derivative of a constant, the number 5, and you just get 0. You could simplify this by recognizing these terms are the same, so you got 2 of them, or pulling out a 1 out of x from all 3 terms, whatever, I don't care. You could simplify this if you want. The point was just supposed to be that, yeah, you could take the derivative of this composite this way. But look what happens when we compose the functions in a different order. Instead of figuring out f of g of x, what if you were asked to figure out g of f of x? Well, let's see. First, I would rewrite it in a form that I prefer that kind of looks like this, where I would write g and then parentheses and then f of x and then end my parentheses. And then just like I did up here, I'd work from the inside out. So I would replace f of x with what it's equal to. f of x is equal to x squared plus 3x plus 5. So instead of writing g of f of x, I can write g of x squared plus 3x plus 5. Switching colors is really obnoxious, but hopefully it's helping you follow all the moving pieces. Now I'm asked to evaluate g of something. I can use this blueprint, which tells me g of x, and change all the x's into whatever my something is. G of x is 10 plus the natural log of x, so g of x squared plus 3x plus 5 would be 10 plus the natural log of, and then instead of writing x, this input, I'm going to write x squared plus 3x plus 5, this input. And you're like, all right, chain rule wasn't that bad. No, we didn't do the chain rule. We haven't done any calculus at all. This is all just pre-calculus. This is just function composition. I'm just building a function by taking two other functions and putting them together. If I put them together in this order, I get this mess, which I could take the derivative of using our previous knowledge. But if I put them together in this order, I get this mess, and I don't think you can take this derivative. At least not with the skills that we have. You take the derivative of 10, that's a 0. But what's the derivative of the natural log of x squared plus 3x plus 5? I don't know. That's not true. I do know. You don't know because I haven't taught you yet. Can you take the derivative of this? Nope. Not without this thing called the chain rule. Fortunately, the chain rule is made just for this purpose, to take derivatives of composite functions. To take derivatives of expressions like you see up here or expressions that you see down here. Sometimes those expressions, if you get lucky, can be manipulated and you could take the derivative using other rules that you already know. But sometimes you don't get so lucky and there's no way to take the derivative without this chain rule. Fortunately, the chain rule will work in both cases, and I think you'll like it better than what we did up here, and you'll certainly like it better than not being able to find the derivative like we have down here. I'll return to these specific examples in just a minute, but let me try to teach you the chain rule with a slightly easier example. First off, here is the chain rule written in our prime notation. What it says is that if you have the composite of two different functions, f of g of x, and you're trying to take the derivative of that composite, then what you do is you take the derivative of the outside function and leave the inside function alone. You evaluate the outside function at the inside function. This is not f prime times g of x, it's f prime of g of x. I'll make that distinction clear when we do an example. And then you're not done, you still have to take the derivative of the inside function. So the two functions, the f and the g, that we end up putting together to create this large function, this and this that we put together to create either this or this, we're going to have to take derivatives of both of those things. There's an f prime and there's a g prime. The g prime, you just take the derivative and you're done. The f prime, you take the derivative and then you change all the x's in that derivative into whatever g of x is equal to. Whoa, that seems really complicated. It's not that bad, it's just hard to write. What we do is we take the derivative of the outer layer, I'll make that more clear as we go, leaving the inner layer completely alone. Here's the derivative of the outer layer, here's the inner layer being left completely alone. But then you're not done, you have to multiply that by the derivative of the inner layer. Here's the derivative of the inner layer. That's a lot of talking. Let me show you an example. If you took the function f of x equals x to the 8th power, and the function g of x equals x squared minus 9, and you compose them together, if you found f of g of x, then what you would do is, starting from the inside out, you replace g of x with what we see written right here, the x squared minus 9, and then you would evaluate f of x squared minus 9, which is something that you can do because you have the blueprint for f of x right here. F of x is x to the 8th power, so f of x squared minus 9 would be x squared minus 9 to the 8th power. The point that I'm trying to make is if you take these functions and you compose them together in this order, you get x squared minus 9 to the 8th power. Pretend you didn't do any of that work at all. Pretend I just started you with this question right here. Would you be able to look at this expression, the x squared minus 9 to the 8th power, and see an outer layer and an inner layer? The trick to using the chain rule is being able to take a question like what's written right here and being able to see this outer layer stuff being raised up to the 8th power and this inner layer, the x squared minus 9. And I know outer layer and inner layer aren't very concretely defined. So if you want a concrete definition, I have to go back here and be like, well, if you compose them back together, that's what you'd come up with. They're the functions defined here and here that when you put them together in this way, leave you with this answer. But you're not going to want to do this function composition every single time you have one of these problems. You're going to want to be able to look at this and see the 8th power and see the x squared minus 9. And that skill, being able to see those, is going to take a long time. And it's going to be the challenge of the chain rule. But once you can see those, the derivatives are easy. The way we take this derivative is we first take the derivative of the red stuff. And you're like, what the hell do you mean taking the derivative of the red stuff? Well, pretend that this was just x to the 8th power. It's not, but pretend all the blue stuff was just a variable. Well, then the derivative would be 8 times that x to the 7th power, right? Using the power rule, the derivative of this outer layer is 8 stuff to the 7th power. The f prime in f prime of g of x is the 8 and the 7. I want to take that derivative and evaluate it at g of x. In other words, I want to take this x squared minus 9, the g of x, and leave that completely alone on the inside in here. What a lot of students do is they take the derivative of the red stuff, 8 and 7 up here, and then they take the derivative of the blue stuff also and write 2x in here. Don't do that. We don't want f prime of g prime of x. We want f prime of g of x. Take the derivative of the red, not the blue. Leave the blue alone. You're like, whoa, you never take the derivative of the blue? No, you absolutely do, but not until this next step. Not until we multiply by g prime of x. So we've taken care of the red stuff. We still have to take the derivative of the blue stuff. We want to multiply that answer by the derivative of x squared minus 9. The derivative of x squared minus 9 is just 2x. So my final answer would be 8 times x squared minus 9 to the 7th power times 2x. And yeah, as is often the case, you can clean this up a little bit and call it 16x times x squared minus 9 to the 7th. But I'm not so worried about that now. I got to pick my battles. And my battle here is being able to see the chain rule. It's really hard to see these different layers, and that's going to drive you crazy. But when you get to the point where you can look at this and see this as different from this, the chain rule becomes pretty easy. Take the derivative of the 8 part, there's the 8, there's the 7, leave this alone, and multiply that by the derivative of the x squared minus 9 part. I think the only way to really get a grasp of this is to get a lot of repetition. So let me do a few more of these examples, wrap up this intro video, and then show you some examples kind of the next level. What if you were asked to take the derivative of the square root of e to the x plus x? First, a little hint. Whenever you see a radical, we don't have derivative rules that deal with square roots, but taking the square root of something is the exact same as raising that something to the 1/2 power. So instead of writing this as the square root of e to the x plus x, maybe write it as e to the x plus x all raised up to the 1/2 power. And yeah, I color coordinated things to help you see the different layers, but eventually you'll want to get to the stage where you can see the different layers without the different colors. When I think it's reasonable to be able to see those different layers, I'll stop doing the color coordination. But for now, I want to show it to you because I know how hard this is on students. Let's try to take this derivative. If we're taking the derivative, first we take the derivative of the outside part. Stuff to the 1/2 power. The derivative is, bring that 1/2 down in front, subtract 1 from that exponent to get negative 1/2. There's the power rule part. And then leave the stuff alone. E to the x plus x. Don't take the derivative in here. Just take the derivative of the red, leave the blue alone. Then multiply that by the derivative of the blue. What's the derivative of the blue? The derivative of e to the x plus x is e to the x plus 1 because the derivative of e to the x is e to the x and the derivative of x is 1. My final answer for the derivative of the square root of e to the x plus x is 1/2 e to the x plus x raised up to the negative 1/2 power times e to the x plus 1. And yes, you could rewrite this if you wanted, get rid of negative exponents, put radicals back in, but I'm not going to bother. Be really careful with these parentheses because we have 2 terms here. If you don't put the parentheses in, all this stuff only hits the e to the x, not the plus 1. You need the parentheses so it hits both, and it has to hit both because g prime of x gets multiplied by this entire thing. I started this video with these 2 different examples where I composed functions together, and then in one case I could take the derivative, and in one case I couldn't. Let's take both those derivatives again, but now we'll use the chain rule. Pretend I didn't give you any function composition, anything. I just said figure out this derivative. And maybe I was a little bit more careful with my parentheses. I said the derivative of this entire thing. Figure it out. Well, there's lots of ways you could figure it out, but one way would be, all right, I'm taking the derivative of something plus something plus something. So my sum rule tells me that I can just take the derivative of each of those things individually. So here's the derivative of the first thing. And for the second thing, maybe I can take this 3, this constant, and pull it out in front using my coefficient rule. And then for the third thing, I got the derivative of the 5. Here's my 3 different terms, 1, 2, and 3. And in that second term, I took the coefficient and pulled it out in front. Note that in the first term, I color coordinated things really carefully for you, because in the first term, you're going to want to use the chain rule. The derivative of stuff squared. We bring the 2 down in front, and we subtract 1 from the exponent, so raise it up to the first power. No, you don't have to write this 1 right here. I'm just writing it to try to help you follow the different pieces. That's the derivative of the red layer. You leave the blue layer completely alone, and then you multiply that answer by the derivative of the blue layer. The derivative of 10 plus the natural log of x is 0 plus 1 over x. In other words, 1 over x. The derivative of this first term is this mess right here. The second term, I don't need any chain rules. I get this 3 times the derivative of this sum. The derivative of the sum is the sum of the derivatives. The derivative of 10 is just 0. The derivative of natural log of x is 1 over x, so I get 3 times 1 over x. And then the derivative of this constant over here is 0. Really, none of this stuff is interesting. It's just the color coordinated part that's interesting. In order to figure out this derivative, we had to use the chain rule on this red layer. It's going to bother me to look at this with the 1 up here in the exponent, so I'm going to rewrite this, but really you don't have to. One way you could rewrite this is 20 plus 2 times the natural log of x, if we take this 2 and distribute it through, divided by x instead of times 1 over x. Plus, instead of this is a 3, think about it as 3 over 1. And 3 over 1 times 1 over x gives me 3 over x. And then I'm not going to write the plus 0. Yeah, I could put the numerators together because I got a common denominator. So I guess I'll do it. 23 plus 2 times the natural log of x divided by x is as far as I would go trying to simplify this thing. But really, this is a perfectly acceptable answer up here. Compare what we just did here to what we did up here at the start of the video. Maybe what we just did is a little bit easier because you didn't have to use the product rule. And you're like, nope, chain rule, way harder. I much prefer the product rule. Okay, even if you're in that boat, consider this example. You can't do this with the product rule. We don't have a way of figuring this out without the chain rule. Fortunately, with the chain rule, it's pretty doable. Let me show you how. The way to look at this is to see 2 different terms, 10 plus all this stuff. So I get the derivative of the 10 plus the derivative of all this stuff. And it'd be awesome if you could look at all this stuff and see an outer layer and an inner layer. The outer layer being the natural log of all this stuff, and the inner layer being that stuff, the x squared plus 3x plus 5. It'll take a while to get comfortable with the red and the blue, which is why I'm still making it red and blue for you. Let's evaluate this derivative. The derivative of 10 is just 0, so I can ignore that. The derivative of the natural log of all this stuff. Well, if it was the derivative of natural log of x, it would be 1 over x. But it's not the derivative of natural log of x. It's the derivative of all this stuff. So I don't want 1 over x. I want 1 over all this stuff. Taking the place of the x is all this stuff. Wait, why? Because this is f prime of g of x. It's not f prime of x. It's f prime of g of x. I'm figuring out my derivative and I'm evaluating it at g of x. I'm putting the g of x in where I would have otherwise put the x in. It's 1 over, and I think I like this in blue, x squared plus 3x plus 5. Nice, that's it? That's your answer? No. This is f prime of g of x. I still have to multiply that by g prime of x, the derivative of this thing. The derivative of x squared plus 3x plus 5, you might be able to just see is 2x plus 3. This is my answer. Could stop right here, or you could rewrite this as 2x plus 3 divided by x squared plus 3x plus 5 and say that this is a prettier form of your answer. I don't care. Really what I care about in this video is this step, this chain rule step, which again is really challenging, but the good news is I recognize how hard it is. So what I'm going to do is just make example after example after example, because I know from learning this on my own that the only way to really wrap your head around the chain rule is a ridiculous amount of repetition. So we'll get that in these videos.